All right, so I just want to go over a couple things about the test on Tuesday before we get started with new material. So the test is made, it's posted in my math lab. You are not going to see it though until Tuesday, so don't be concerned that it's not there. It's there. It's going to pop up on Tuesday at 12 a.m., which is really like Monday at midnight. So you'll have between Tuesday at 12 a.m. and Wednesday at 11:59 p.m. to take the exam. So a 48-hour window there. You can take it at any time. You get 2 attempts on the exam, and I'll take the highest score out of the 2. But I won't give any partial credit. However, I will go back through and look at everybody's tests and see if there's any kind of syntax error where like you wrote x equals 5 and they only wanted the 5, or you wrote 5 and the other way around, as long as it's not a notational thing. We will not meet for class on Tuesday, so you'll just focus on your exam for Tuesday, and we'll meet for class on Thursday. You have homework due on Monday night, and the bonus quiz is due, I believe it's at 8 a.m. on Tuesday. Also, you'll need to submit another Dropbox quiz on Monday nights. I'm going to be grading the Dropbox quizzes that you already submitted. That's on my agenda to do tonight and tomorrow, so be looking for that. I'll probably send out an email when I have them graded so you know when to go into the Dropbox and check for your feedback. Anybody have any questions on the test at all? Also, I typically have office hours on Monday nights. Next week, I need to have it on Tuesday night because I have a meeting on Monday night that I can't get out of. So I'm going to push my office hours to Tuesday. I will post an announcement in D2L reminding you guys about that. Also, just wanted to mention that if my virtual office hour times don't work for you, you can always request one by appointment as well. Anybody else? Any questions, anybody?
So just to make sure, we can take the test on Wednesday, right?
Yes, but I would encourage you to take advantage of the fact that I'm giving you 2 attempts on the exam. So if it was me, I would do one on Tuesday and then do it again on Wednesday.
Okay.
You can only review the feedback on the exam immediately after you take it. So when you get your score, don't just quick X out of it. That is the only opportunity you're going to have to see which problems you got wrong and what the correct answers are. So I would even plan for, another 30 minutes after you take the exam to look through it, write down what you got wrong and things like that in preparation for your second exam.
Okay, thank you.
Anybody else? All right, well, let's get started on Unit 4 then. So the Unit 4 begins with inverse functions, but before we can talk about inverse functions, we have to talk about a special type of function called a one-to-one function. A function f of x is 1-to-1 if for x1 and x2 in the domain of f, if x1 and x2 are different, so that's what it means, x1 not equal to x2, then f of x1 will not be equal to f of x2 either. Equivalently, if f of x1 is not equal to f of x2, then x1 won't be equal to x2. That is, no 2 inputs map to the same output. When I first introduced functions, when I'm teaching it at all, but even when we reviewed it back in Unit 2, I gave a real life example of a function being people and their birth dates, that one person cannot have 2 different birth dates, but 2 different people could have the same birth dates. That's an example of a function. A real life example of a one-to-one function involves people and their social security numbers. Each person has exactly 1 social security number, and no 2 people have the same social security number. So that is a one-to-one function. 1x maps with 1y, no repeats whatsoever. So we're going to look at ordered pairs, graphs, and equations and determine whether they are one-to-one functions or not. So we'll start with ordered pairs. Remember that when we're thinking about just a regular function, to determine whether a relation is a regular function, we look at the x values of the ordered pairs. If the x values repeat, then the relation is not a function. Well, that's true for one-to-one functions. One-to-one functions just have an additional stipulation. To determine whether a function is one-to-one, you also have to look at the y values of the ordered pairs. If the y values repeat, then the function is not a one-to-one function. So in summary, what you have to do is make sure that there are no repeats at all. No repeats for the x, no repeats for the y in a one-to-one function. So we're going to look at each set of ordered pairs here, determine whether it is a one-to-one function, and then some sort of justification about that. So let's take a look at our first set of ordered pairs. In order to be a one-to-one function, there have to be no repeats. No repeats in the x's, no repeats in the y's. So do we have any repeats?
No.
No, we don't. So this first function is one-to-one. Typically, when we denote one-to-one, we don't actually write out like O-N-E-T-O-O-N-E. We just write like 1-1. So this is a one-to-one function. And our justification is each x value is paired with a different y value. Questions at all? All right, let's take a look at our next example. We want to determine whether this is a one-to-one function. So we're looking for repeats. Do we have any repeats?
Yes.
We do. Notice that this y value of 6 is paired with two different x values. This would be the same as saying that two different people had the same social security number, and we know that cannot happen. So we're going to say this is not a one-to-one function. And our justification is the y value of 6 is paired with two different x values. Questions, anybody, on determining whether a set of ordered pairs is a one-to-one function? All right, let's move on to graphs. Recall, for a graph to be just a regular function, it has to pass the vertical line test. Well, in order for a graph to be a one-to-one function, not only does it have to pass the vertical line test, but it also has to pass what's called the horizontal line test. And the horizontal line test is super similar to the vertical line test. The horizontal line test says that if you can draw a horizontal line that intersects your graph at more than one place, then it's not one-to-one. So let's take a look at these two graphs and determine whether we have a one-to-one function. This first one is a parabola, so we start with the vertical line test. Does it pass the vertical line test? Sure does. There's nowhere that I can draw a vertical line and it hit the graph more than once. But to be one-to-one, it also must pass the horizontal line test. Notice that when I draw in a horizontal line, it does hit the graph more than one place, here and here. So it fails the horizontal line test, which means that it is not a one-to-one function. And our justification is that it fails the horizontal line test. Questions on that? Well, let's take a look at our next graph there. That's the graph of f of x equals 1 over x. Remember that that has both a horizontal and a vertical asymptote. Our graph is never going perfectly vertical or perfectly horizontal. It's always getting closer and closer to that vertical and horizontal asymptote. So is this going to be one-to-one? Does it pass our horizontal and vertical line tests?
Yes.
So there's no place that I can draw a vertical line and it hit more than once, because again, remember, as it's approaching that vertical asymptote, it's never going perfectly vertical. It's always getting closer and closer. And if we do our horizontal line test, never does it hit more than once there as well. So yes, this is a one-to-one function. And we're going to say that it passes the vertical line test and the horizontal line test. Questions on determining whether a graph is a one-to-one function? All right, let's move on to graphs as equations. Now, when we talked about functions earlier in the course, our graphing abilities were very limited. So to determine whether an equation was a function, we did a lot of like solving for y and see if we got more than one answer. Well, now you know how to graph a ton of stuff. So what I would do at this point, if we want to determine whether an equation is a one-to-one function, is I would draw a picture of the graph and then use our horizontal and vertical line test to determine whether or not it's one-to-one. Let's start with f of x equals x plus 2. What does the graph of this look like?
It's a line.
Could you be a little more specific?
Slope of 1, y-intercept of 2.
There we go. So there's the graph of our equation. Does that pass the horizontal and vertical line test?
No. Oh, yeah.
Passes vertical. Passes horizontal. We do indeed have a one-to-one function. Great. G of x is equal to the absolute value of x minus 1. So let's think about what the graph of that looks like.
It's going to be a V, so it can't pass the horizontal line test.
This is our parent absolute value function, which is a V shape. It's and shifted down 1. And Naomi's right that if we draw a horizontal line, we see that it intercepts at more than one place. So this is not a one-to-one function. Be sure that you are checking both vertical and horizontal, because it could pass the horizontal and fail the vertical. It has to pass them both. Okay. Any questions on determining whether a graph is one-to-one? Any questions on one-to-one functions at all? Because that's my intro for one-to-one functions before we move on to inverse functions. All right. So I'm back to my diagram here with people and social security numbers. If a function is one-to-one, then the function maps every x to one and only one y, and no two x values map to the same y value. This implies that there is a one-to-one correspondence between the domain and range values of the one-to-one function. So one person, one social security number. So if I have this function f that maps people to their social security number, people ends up being the domain of this function, while social security numbers end up being the range. Unlike our birth dates, see, if somebody said, all right, well, who was born on my birth date, a whole bunch of names would come up. But if somebody typed in your social security number into a computer, only your name is going to come up because of that one-to-one correspondence. That one-to-one correspondence allows us to map these social security numbers back to the person. This function that maps the output of one function back to its input is called the inverse function. And the way that we indicate inverse in math, it looks like this little exponent of -1. It is not an exponent. It's just the notation we use is a superscript up there of -1. Now, for our inverse function, social security numbers becomes the domain of that function, while people become the range. Our diagram shows us that people, it has two different, what do I want to say? People plays two different roles depending on which function you're looking at. If you're looking at our function f, people is the domain, but if you're looking at our inverse function, people is our range. So the domain of our function f becomes the range of our inverse function. We can make a similar conclusion about social security numbers. Social security numbers, well, that's the range of our function f, but it's the domain of our inverse function. That fact is going to be really important for us as we proceed through this section and the rest of the unit. So here we have our properties of inverse functions, and our very first property is that property that we just now talked about, that we just discovered, that the domain of the inverse function is the range of the original, and the range of the inverse function is the domain of our original. We are going to use this a lot. Property number 2 says that if you take a function and perform function composition with its inverse, you're always going to end up with x. The reason that there are two parts to that second property is that function composition is not commutative. So we have to write it both ways. So I want to go back up to our diagram and we'll see how that property number 2 works. If I start with a function f, right, we start with its domain or x values. If I apply function f and then apply the inverse function, it gets me back to where I started. And where I started was at x values. So f composed with f inverse brings me back to x. Similarly, if we start over here with the domain, the x values of our inverse function, if we apply the inverse function first, and then the regular function, we get back to where we started, and where we started was with x values, with a domain. So that's our property number 2. We really just use property number 2 to verify whether 2 given functions are inverses of each other or not. Honestly, I don't use it a ton. And then lastly, the graphs of inverse functions are symmetric with respect to the line y equals x. And that's the diagram I have there on the right. I have the line y equals x in the black dotted line. And then I have my function f in red, the inverse function in blue. And we see that we have the mirror image on either side of that line. Questions at all about our 3 properties of inverse function? Okay, well, here I'm going to give you a function as a set of ordered pairs, and I'd like you to find the inverse function. Well, the very first thing you need to do is verify that the function you've been given is 1-to-1, because if it's not 1-to-1, then the inverse function doesn't exist. And I promise there's going to be somewhere where I give you a function that is not 1-to-1, and I ask you to find the inverse of it. It's really important that we understand and remember that only 1-to-1 functions are eligible to have an inverse. So let's take a look at that g of x. Is that going to be a 1-to-1 function?
Yes,
And how do you know?
because none of them repeat.
Because we have no repeats. So, all right, great. Well, how do I find my inverse from here, knowing that it exists? We're going to use that first property of inverse functions. See, this first property says that the domain of the inverse function is the range of the original, and the range of the inverse is the domain. So basically what's happening there is that the x and the y values are flip-flopping, because we know that domain is x values while range is y values. So all we need to do here, don't make it hard. We're going to just simply interchange x and y values. Don't change the sign. That's the mistake I see the most, is that people change all the signs. Don't do that. We're flip-flopping the numbers. 0, 2, 3, 4, -7, -5. And that is it. Questions, anybody? All right, well, in this next example here, I have given you the graph of a function f of x, and I want you to graph the inverse. Our property number 3 tells us that a function and its inverse is symmetric about the line y equals x. It can be really difficult to try to reflect a curve about a diagonal line and end up at the right points. So what I suggest you do to help yourself is start by identifying several points on your original function. So here we have -2, 1, 2, 3, and 7, 4. And then we're just going to interchange those ordered pairs to get our inverse function. So points that go with F inverse are going to include 1, -2, 3, 2, and 4, 7. So we'll plot those points, connect them, and we'll have the graph of our inverse function. Now notice that the arrow was with our ordered pair 7, 4, so our arrow should be with our ordered pair 4, 7 when we draw this in. And there we go. There's the graph of our inverse function in blue. And I can see, I mean, although my graph is not perfect, that it looks pretty darn symmetric about that line, y equals x. Questions, anybody? In our next two examples, we are going to use that second property of inverse functions, the function composition, to determine whether or not f and g are inverses of each other. Using that property number 2, we're going to do function composition both ways. If we end up with x both times, then these two functions are going to be inverses of each other. If I don't get x both times, well, then they're not inverses of each other. So let's start with f composed with g. That's going to be f of g of x. That's f of 3x plus 2. Everywhere we have an x and f, we're going to replace it with the quantity 3x plus 2. That's 3x plus 2 minus 2 all over 3. Combining our like terms in the numerator, we get 3x over 3, which can be simplified down to just x. Questions on that function composition? All right, now let's go the other direction. Now, if it had not worked for that first direction, I would not even waste my time checking the other direction because it has to work for both. So now we're finding g of f of x. Everywhere we have an x in g, we're going to replace it with x minus 2 divided by 3. So that's going to be 3 times the quantity, 2x minus 3 plus 2. I'm multiplying a fraction by not a fraction, so I'm going to take this 3 and throw it over 1 before I multiply. I can cross cancel out those 3's. It's going to leave me with just x minus 2 plus 2. And when I combine like terms, I get x. Since I got x for both function compositions, we can conclude that f of x and g of x are inverses of each other. Questions, anybody? All right, let's try another one. Start by looking at f composed with g. That's f of g of x, which is f of 5 plus x to the third. Everywhere I have an x and f, I'm going to replace it with that binomial. So I'm going to have 5 minus this whole thing, 5x, I'm sorry, x plus, oh my goodness, 5 plus x to the third. And then all that's raised to the 1/3 power. Be sure to put those parentheses in there because we're now going to have to distribute that negative. I can combine those like terms. It's going to leave us with negative x to the third raised to the 1/3 power. And now we need to simplify that. Excuse me. Remember that to the 1/3 power is the same as a cube root. You might also want to recall that negative x to the third is the same as -1 times x to the third, and all that's raised to the 1/3 power. When we have an outer exponent with multiplication on the inside, that outer exponent goes to each one of the factors. And then that -1 to the 1/3 power is the same as the cube root of -1. And with the x, right, we're just going to multiply our exponents. 3 times the third is just 1. So we get x. Last thing we need to think about is what's the cube root of -1? Can we have a negative under a cube root?
No.
So a square root or any even indexed radical are the ones that we can't have a negative underneath. We can have a negative under any odd indexed radical. It just so happens that our answer is going to end up being negative. So the cube root of -1 is simply -1. So we're ending up with -1 times x or negative x, and that is not what we're looking for. We have to get positive x on both function compositions for them to be inverses of each other. So we can conclude that f of x and g of x are not inverses of each other. Questions, anybody? All right, well, we're going to spend the rest of our class today. I'm going to give you a function, and you are going to tell me what the inverse of that given function is if it exists. We're also going to state the domain and range of the inverse function. So here's our procedure for finding the inverse of a given function. The first thing you need to do is verify that the given function is actually 1-to-1, because only 1-to-1 functions are eligible to have an inverse. The way that we're going to verify that is we are going to draw ourselves a graph and see if it passes both the horizontal and vertical line tests. You want to draw a pretty accurate graph here, even more so accurate than we were doing before, because if it is a 1-to-1 function and we do find the inverse, we're going to use that graph that we drew in the beginning to get the domain and range of the inverse function. All right, excuse me one second. I'm going to go hush my kids. Sorry about that. Okay, so we want to find the inverse of f of x equals 7x minus 3. The first thing we need to do is verify whether or not it is 1-to-1. We want to draw a relatively accurate graph to make that determination. So what can you tell me about the graph of this?
The y-intercept is -3.
The y-intercept is 0, -3. I agree.
And your slope is 7.
And our slope is 7. So there is the graph of our function. Is that 1-to-1?
Yes.
Sure is. It passes both the horizontal and vertical line tests.
I have a question.
Yep.
So on the test, do we have to draw the graph even if it's a linear equation?
Okay, well, since it's going to be a MyMathLab test, I'm not going to see any of your work. I'm only going to see your answers, so no. But if we were if we were doing our traditional test, yes, I would want to see it.
Okay.
All right, well, now that we know that we are 1-to-1, we're ready to continue with our steps. So step number 2, we're going to take our function out of function notation by simply replacing f of x, g of x, h of x, whatever, with y. Next, we are going to interchange x and y, just like we did with our sets of ordered pairs. Next, we're going to solve for y. Once we have solved for y, whatever we have left is our inverse function. So lastly, we're going to put it back into function notation by replacing y with f inverse of x. All right, so let's take it out of function notation. You know what? I think I'm going to number the steps here. So this drawing over here was step number 1, where we verified that it was 1-to-1. In step number 2, I'm going to take it out of function notation by replacing the f of x with y. Our third step is to interchange x and y. And now we need to solve for y. What should we do to solve for y?
Set x equal to 0.
No, we're just trying to solve for y. So you're trying to make it harder. What you're thinking of is y-intercept. So all we're trying to do is isolate that y. So what are our linear solving moves?
So would you move 3 to the other side? You would add 3 to x?
You got it. We're going to add 3 and divide by 7. And now that we have solved for y, we have found our inverse function. So here's our step number 5, putting it back into proper notation. F inverse of x is going to be equal to x plus 3 over 7. Questions on anything we did there? Last thing we need to do is identify the domain and range of this inverse function. We're going to be using our property number 1 that says the domain of our inverse function is the range of our original function, and the range of our inverse function is the domain of our original function. We're going to be using this property coupled with the graph that we drew in the very beginning to get this information. So the domain of F inverse is the range of the original. We have the original graphed there in red. What's the range of that red graph?
Negative infinity to positive infinity.
Perfect. And then the range of our inverse function is the domain of our original. Taking a look at the graph of our original, what's the domain of that?
Negative infinity to positive infinity.
Same thing. So there we go. Questions on finding the inverse function or the domain and range? All right, well, let's do like 6 more of them and I will get them to increase in difficulty. Really, the only increase in difficulty comes with drawing the graph to begin with, and maybe the algebra techniques that need to be used in our step number 4 to solve for y. But the procedure stays the same. Here we have the function g of x equals the square root of x minus 1. We want to verify that it's 1-to-1 by drawing the graph. And again, we need to be relatively specific here. It doesn't have to be perfect, but it's really important that we identify the starting and stopping points of this graph. What does the graph of this g of x look like? And I know you're doing your like sweeping hand motions that I can't see. So how has this graph been transformed? Isn't this our square root function that looks like this? And it has been transformed by shifting it 1 unit to the right. So we get this right here. Again, it doesn't have to be perfect, but it's really important that we know the starting and stopping point of each of these. Is the graph of that function 1-to-1?
Yes.
It is. It passes both the horizontal and vertical line test. So this is indeed 1-to-1. That means that we can find the inverse. So we'll start by taking it out of function notation. Then we're going to interchange the x and the y. And then we have to solve for y. What algebra do we need to do to solve for y?
Square both sides.
We're going to start by squaring both sides. That'll give us x squared on the left, and then our square and square root cancel on the right. Continuing to solve for y, all we need to do is add 1 to both sides. We get x squared plus 1 to be equal to y. And now we need to put it back into our function notation. We get that g inverse of x is going to be equal to x squared plus 1. Any questions on coming up with the inverse? All right, well, domain and range are next. The domain of our inverse function is equal to the range of the original, and the range of our inverse function is equal to the domain of our original. So starting with the domain of G inverse, that's the range of our original, and we have our original graph there in red. What is the range of that graph?
0 included to infinity.
Including 0 to positive infinity. And then to get the range of our inverse function, it's going to be the domain of the original function. Again, graph there in red. We just need to take a look at it.
Included 1 to positive infinity.
Questions at all on finding the domain and range? Now, a function and its inverse should both be 1 to 1. If you look at our inverse function here, we have x squared plus 1, which is a parabola that has been shifted up 1 unit. That graph definitely fails the horizontal line test. So some of you might have been thinking about that. Well, that's true, but notice that we have a domain restriction for our inverse function. Our domain for the inverse is only from 0 to infinity. So we're only considering this half of the parabola, not this half. So if we only look at that 1/2 of the parabola, it does pass both the horizontal and vertical line tests. Questions at all?
So should we always double check if we do get an answer that doesn't pass the vertical or horizontal line test?
Yeah, I would double check, make sure you had the right range there, because maybe you forgot to see whether it was 1 to 1 in the first place or something like that. Anybody else? All right, let's try another one. This time, f of x is equal to 4 over x minus 1. This is a rational function. This will be good review for you for your test on Tuesday. Coming up with the graph of this. Because we're not worried about the graph being perfect, all we really need to do is find the asymptotes. So what can you tell me about the asymptotes of this?
It's at +1. There's a break,
Okay, could you be, what type of asymptote?
a vertical.
A vertical asymptote at x equals 1. I agree. How did you come up with that?
Because 1 is the 0.
Of our denominator, right? So to find our
Yes.
vertical asymptote, remember we are using the zeros of our simplified denominators. We know we're going to have a vertical asymptote right here at +1. How about any horizontal asymptotes? That's where we're comparing the degree of the numerator with the degree of the denominator.
Are they equal?
Well, equal would mean that we had x to the first on the top and x to the first on the bottom. We do not have x to the first on the top. So it's actually degree 0 on the top and degree 1 in the denominator. So we're in the situation where the degree of the numerator is less than the degree of the denominator. What does that tell us about our horizontal asymptote?
It's going to be at y equals 0.
It's going to be at y equals 0. This one, I know we didn't do rational functions when we did graph by transformation, but this is actually just our parent f of x equals 1 over x, that it's been transformed by being shifted 1 to the right and vertically expanded by 4. But you could always get a couple test points just to get your graph in. Usually when you have one vertical and one horizontal, your little loops here are either opposite, so it could be like there and there, or here and here. But every once in a while, they're on the same side of the horizontal, so we just need to kind of figure out, where it's at. Because again, we don't need a perfect graph. So I'm going to plug in a number to the left of the vertical asymptote and one to the right of the vertical asymptote, and then that'll kind of tell me where my little swoops are. So to the left of my vertical asymptote, I'm just going to plug in 0 for x. If I plug in 0 here, I'm going to get 4 over -1, which is -4. So since we're down here, that tells me that this part has to be over here. And then plugging in a number to the right of my vertical asymptote, say I plug in like, I don't know, 2. That's going to give me 4 over 1. So that tells me the other one has to be here. Now that I have a graph, is it 1 to 1?
Yes.
Yeah, it is. All right, 1 to 1 function. Now we can proceed with actually finding the inverse. So I'm going to start by taking it out of function notation. I'm going to interchange my x and y value. Now I need to solve for y. Y is currently located in the denominator. So our number 1 priority is to get it out of the denominator. Notice that we have a proportion here. So then I can cross multiply. And we're going to get 4 equals x times y minus 1. Great. So now we've gotten y out of the denominator, but we need to continue to solve for y. Suggestions on what we can do?
Divide x by 4, or divide 4 by x.
We have 2 different options. So we need to get at the y, which is currently like, trapped inside these parentheses. So I need to get rid of the parentheses. And there's 2 options to get rid of the parentheses. We could either divide both sides by x. And since there's nothing else on the side with the parentheses, we can drop the parentheses. The other option would be to distribute the x and then solve for y that way. Either way, we'll get the same answer. So last thing we need to do to solve for y is add 1 over. And we have our inverse function. We're ready to put it in function notation. F inverse of x is equal to 4 over x plus 1. Questions on finding that inverse function? All right, we're ready for domain and range then. The domain of our inverse function is the range of our original. So we're going to take a look at the picture of the graph of our original. What is the range of that?
Negative infinity to 0 excluded union 0 to positive infinity.
That looks great. It's everything except our horizontal asymptote. And that horizontal asymptote's at 0. So now we want to find the range of our inverse function, which is the domain of our original. So we're going to take a look at the graph of our original. What's the domain of that?
Negative infinity to 1 parenthesis, and then 1 parenthesis 1 to positive infinity.
Awesome. All right, there we go. Questions, anybody? All right, we got a couple more. This time f of x equals 2 times x to the third minus 5. We want to start by verifying whether or not it's 1-to-1. So we want to graph this. Oh, what does the graph of this look like?
It's the tall squiggle.
It's the tall squiggle, that's right. How has that tall squiggle been transformed? All right, this minus 5 tells us that we've been shifted down 5. This 2 out in front means we have a vertical expansion by 2. So here we are. Again, it doesn't have to be perfect, but we want it to be pretty close. For those of you who are feeling shaky on your graph by transformation, don't worry. We will be graphing by transformation again starting next Thursday, because I'm going to teach you an infinite number of new parent functions, and we'll be graphing them by transformation. So you'll have the opportunity to brush up. All right, is that a 1-to-1 function?
Yes.
Sure is. So that means that we can go ahead and find the inverse. I'm going to start by taking it out of function notation, interchanging x and y, and then solve for y. I'm going to pause the video and give you guys a minute to solve for y. Go ahead and do the domain and range as well. All right, Taylor, you said that you had an answer. How'd you get that answer? What was your solving process?
So I added 5 to both sides. And then I divided by 2. And then I took the cube root of y and the cube root of the fraction.
Looks great to me. Oh, I forgot my index. Don't do that. Perfect. And I would not waste my time rationalizing this. Like that's fine. That's fine. All right, great. That's our inverse function. F inverse of x is equal to the cube root of x plus 5 over 2. And now we need to state the domain and the range. The domain of our inverse function is the range of our original. So taking a look at the graph, what is the range?
Negative infinity to positive infinity.
Perfect. And then the range of our inverse function is the domain of our original. So taking a look at our graph, what is our domain?
Negative infinity to positive infinity.
There we go. Questions, anybody? All right, just two more. We have h of x equals x squared plus 8. So I want to start by graphing this. What can you tell me about the graph?
It's a parabola, so it probably doesn't have an inverse.
I knew you were coming, right? I was waiting, Naomi, for you to just say, I'm telling you it's not 1-to-1. But he did tell me it was a parabola. Great. So she's exactly right. See, it's a parabola. It's been shifted up 8. So it's going to fail the horizontal line test. So this is not 1-to-1. The biggest mistake that I get from students is that they say not 1-to-1 and they circle it like it's the answer. Well, the question wasn't whether this was 1-to-1. The question was, what is the inverse? So this is not the answer. Our answer is that H inverse does not exist. Questions, anybody? All right, last one. I saved the best one for last. Rational function. So just like before, we want to look for our asymptotes, and then we'll do kind of like a quick spot check.
So there's going to be a vertical asymptote at -2,
Great.
and there isn't a horizontal asymptote.
Well, so we got to compare the degree of the numerator with the degree of the denominator. So notice they're both x to the first. So here we have the situation where the degrees are the same. What do we do when the degrees are the same? We have a vertical asymptote at the ratio of the leading coefficients. So our leading coefficients are both 1. Oh, we're going to have a horizontal asymptote at y equals 1. Questions on the asymptotes? Now we need to figure out where our swoops are, whether they're opposite each other or on the same side of the horizontal or what. So I'm just going to do, some spot checks. I'm going to just choose a point to the left of my vertical asymptote, one to the right of my vertical asymptote. So to the left of my vertical asymptote, I'm just going to choose x equals -3. So if I plug in -3, I get +7. So that tells me this one's up here. And then I'll plug in a number to the right of my vertical asymptote. I'll choose x equals 0. So that tells me this one's over here. All right, is that going to be 1-to-1?
Yes.
Sure is. So that means we can go about finding the inverse. We'll take it out of function notation. we will interchange x and y. So for the first time, x is showing up more than once. So when we do this interchange, y is going to be showing up more than once. And we want to solve for y. Well, you have you've done this algebra technique procedure that we're about to do now, but maybe it's been a while. When you first learned how to solve quadratic equations by factoring, you did this technique. So I will be happy to refresh your memory on this because we will be needing this for solving exponential equations at the very end of the course. So the issue is that the y shows up more than one time. It's linear and it shows up more than once. Well, the first thing I notice is that the y is in the denominator, or at least one of them is. So I'm going to cross multiply to get it out of the denominator. So we get x times y plus 2 equals y minus 4. Now I need to gain access to that second y that's currently located in the parentheses. Just like in one of our previous examples, we have two options. We could either divide by x to gain access to that y, or we could distribute. Now, if we divided both sides by x, it kind of causes a problem because now I got like this weird fraction over here with a y over an x, and it's going to be hard to gain access to this y right here. So I would opt in this example to distribute instead of dividing. So I'm trying to solve for y. I can't just add 4 because we can't say y equals something with a y in it. We need to have just one y all by itself. So here's this technique that you've seen before, but maybe forgotten about it. What we want to do is get all terms containing y on one side. All the terms that don't contain a y, you want to get on the other side. So that's the first thing we're going to do here. So basically, this one needs to come over here, and that one needs to go over there. Xy minus y equals negative 2x minus 4. You'll notice now that we have a common factor of y on the left-hand side. We want to factor out that y. It's going to leave us with y times the quantity x minus 1 equals negative 2x minus 4. Now, we wanted to do this because y now shows up one time and one time only. So we're going to solve for this one and only y. I have to get rid of that parenthesis. The parenthesis is multiplying, so we are going to divide both sides by this x minus 1. We're going to get y to be equal to negative 2x minus 4 over x minus 1. And that'll be our inverse function. We just need to rewrite it now. Might use R. Our inverse of x is going to be equal to negative 2x minus 4 over x minus 1. Questions on any of that algebra? Okay, so domain and range time. And just like with the more basic rational one, we're really just looking at the asymptotes to help us get the domain and range. So the domain of R inverse is the same as the range of R. So taking a look at the graph of R up there, what's our range?
Negative infinity to 1 excluded, union 1 to positive infinity.
All right, so it's everything except our horizontal asymptote. Perfect. And then the range of our inverse function, well, that's the domain of our original. So looking at the graph of our original, what time, geez. What's the domain of our original?
Negative infinity to -2 excluded, union -2 to positive infinity.
And there it is. Questions, anybody on inverse functions, how to find them, how to verify we're one-to-one, how to find the domain, anything like that? All right, well, if you guys don't have any questions, I don't have anything else for you today. We kind of recapped everything for Tuesday, or all of next week, at the beginning of class. So I don't really have anything to wrap up.